Volcanoes. There's something almost hypnotic about them. The way they rise above the landscape, the way lava flows like rivers. A reminder of just how breathtaking this planet can be. They feel alive, ancient, beautiful, and then, without a warning, they can turn into the exact opposite. Powerful enough to flatten forests, bury cities, and turn thriving landscapes into nothing. Just bare, lifeless rock. And yet, in the middle of all this destruction and chaos, you can always be sure of one thing. Life will always return. And this is really the heart of the paradox, because despite their destructive nature, volcanic slopes are home to some of the most biodiverse ecosystems on the planet. Plants, insects, birds, almost every form of life can be found on these slopes. This is Mount Kelud, one of the most violent and unpredictable volcanoes in Indonesia. Over the last 1,000 years, it has erupted more than 30 times, claiming tens of thousands of human lives. Its latest was in 2014, where it erupted with almost no warning. More than 100,000 people were forced to evacuate. And then, just a decade later, its slopes look like this. Green, lush, and full of life. So, just how does this make sense? How does destruction become creation? To find out, we're going straight into the aftermath. We are going to hike this incredible volcano all the way from the base to the crater. And while we do that, I will show you exactly how these volcanic ecosystems work. And it just so happens that Indonesia is practically the perfect place to do this. See, Indonesia has more active volcanoes than any other country in the world. To see why, we need to zoom way out. The Earth's crust is made up of massive slabs called tectonic plates, like pieces of a giant jigsaw puzzle. Indonesia sits right where three of them collide: the Eurasian, Australian, and Pacific plates. And that's no coincidence. It's exactly at these boundaries where magma can reach the surface from deep below. Kelud, for example, lies right here on the island of Java. Here, the Australian plate collides with the Eurasian plate, and because it's denser, the Australian plate sinks beneath the Eurasian one, a process known as subduction. As the Australian plate sinks into the mantle, seawater trapped in the oceanic crust is carried down with it. That water affects the surrounding rock by lowering its melting point, which causes it to melt into the substance we know as magma. This magma is lighter than the material around it, and thus it rises through the crust. When it reaches the surface, it creates what we call a volcano. Now, Kelud is what's known as a stratovolcano, a type of volcano built up over time by layers of hardened lava and ash, with each layer marking the memory of an eruption. Just 1 to 4 kilometers beneath the surface lies its magma chamber, the reservoir where molten rock from the sinking oceanic plate collects. Compared to other volcanoes, Kelud's is surprisingly shallow. Other volcanoes often have their magma chambers 4 to 9 kilometers below the summit. And this detail is actually extremely important.
You see, the deeper into the earth you go, the more weight is pressing against you from above. This means that the pressure is significantly higher deeper below ground. And as a consequence, the pressure within Mount Kelud's magma chamber is way lower than other volcanoes with deeper magma chambers.
Because the pressure is lower, gases inside the magma expands. This increases the internal pressure in the chamber. As more magma rises and gas builds up, pressure steadily increases until the rock above it can no longer contain it. When that threshold is crossed, the chamber ruptures in a violent eruption.
This is the usual cycle of Kelud's eruptions. However, things don't always play out this way. In 2007, a lava dome emerged within the crater. This is a bit unusual for this specific volcano.
See, not all magma behaves the same. Its composition, especially its water and silica content, determines how fluid it is. Magma rich in water and low in silica tends to flow easily, while drier, silica-rich magma is thick and sluggish. In 2007, Kelud's magma was unusually dry and silica-rich. So instead of pressure building fast as usual, the magma only rose slowly and hardened near the surface, forming a dome. That dome remained for 7 years, where the pressure again got high enough for a new eruption to tear it apart.
So when a shallow magma chamber is combined with viscous magma, we get frequent eruptions. That makes sense, but what really makes Mount Kelud unique is the existence of a crater lake. Now, this might not seem like a big deal, but it has some pretty wild consequences.
As pressure builds within the volcano, magma slowly moves closer to the surface. If the surface rock contains just a tiny crack, the water from the lake will eventually seep through and reach the hot magma. This contact makes the water vaporize instantly and releases huge amounts of energy. As all of this pressure is relieved, the lake is catapulted into the air. Here it mixes with ash and rock, and when gravity pulls it back down, extremely destructive floods of essentially boiling concrete are created. These floods are called lahars, and they can travel down the mountain, reaching speeds up to 60 kilometers an hour.
In 1919, Kelud erupted, forming one of the most destructive lahars in recorded history, killing more than 5,000 people and flattening almost the entire city of Blitar. Following the deadly eruption, the Dutch government, who were running things around here at the time, decided to construct tunnels that would lead water from the lake and into nearby river systems. By doing this, less water would accumulate in the lake, and thus less destructive lahars would be created. This was a huge step in human-induced volcanic hazard mitigation, and these tunnels have potentially saved thousands of lives.
But from nature's perspective, this level of destruction isn't a catastrophe. It's just natural clearance. Kelud doesn't just destroy, it resets. And somehow, that reset is exactly what allows life here to flourish. See, whenever a landscape is stripped back to bare rock like this, something predictable begins to happen. A process known as ecological succession. Imagine you're building a house from scratch. You have to start with the foundation. That's what everything else rests on. Then comes the framing, the skeleton that gives the house its shape. Once that's done, you can put up the roof and exterior walls. And finally, you insulate it and add the finishing touches. Incredibly enough, nature actually follows a very similar and predictable pattern. First, the pioneer species arrive. They create the foundation by slowly breaking down the bare rock, and over many generations, their remains mix with tiny rock particles to form the first traces of soil. Next, the intermediate species, like shrubs and small trees, arrive. They act as the framing. They add structure and complexity, enriching the soil and casting the first patches of shade. And finally, the finishing touches can be added. Shade-tolerant trees that grow in these shaded patches, completing the system and forming what's known as a climax community. In ecology, we call this process of predictable regeneration succession.
And just like a house increases in complexity, eventually adding rooms, plumbing, lights and so on, these ecological stages represent levels of increasing complexity as well.
In the early stages of succession, the environment is simple, consisting of mostly the same few species. But as the system develops, more conditions are created. Shaded areas, richer soils, and more stable microclimates. By the time we reach a climax community, it's like having a fully built mansion with kitchens, bedrooms, bathrooms, and storage spaces. Each room designed for specific use. For exactly this reason, climax communities are often able to sustain higher biodiversity. More layers, more variety, and more opportunities for life to specialize and coexist. Which brings us straight back to the paradox. Because on volcanic slopes, nature rarely has the time to reach fully developed climax communities. The next eruption interrupts the process long before it gets there. No single species can adapt to that level of destruction. So instead, life adapts collectively, not by resisting destruction, but by rebuilding after it.
Now, you might have heard that volcanic landscapes are incredibly fertile, creating some of the richest soils on Earth. So you might be wondering, why the slow start? If the rock is full of nutrients, why don't the bigger plants just move in right away?
And that's a good question. But you have to think of the volcanic rock not as the foundation itself, but as all the raw materials necessary to build it. Think of them as a big pile of lumber, concrete, pipes and wiring all jumbled together. All the materials are there, but they have to be processed first. This is the exact problem plants face. The volcanic rock is packed with essential minerals, such as phosphorus, potassium and calcium, but they are chemically locked away. A plant can't just reach its roots into solid rock and pull out nutrients. any more than you can build a functional kitchen by just staring at a pallet of pipes and boards.
So how does the construction begin? It starts with the only crew that can handle these raw materials, the pioneer species. This area right here is absolutely packed with different kinds of mosses, and they occupy a pretty essential role within this system. You can think of them as the specialized processing and demolition crew.
They are the ones who start cutting the lumber to size, mixing the concrete and separating the pipes. And the way they do it is really quite fascinating. See, these plants don't require soil to grow. They can absorb nutrients and moisture directly across their surface. They don't have true roots like other plants, and instead use tiny structures called rhizoids to anchor themselves to the rock. Many mosses release organic acids that chemically react with the rock, dissolving minerals and freeing up nutrients. When these minerals mix with the decaying moss, the very first traces of soil begin to form.
Now, whenever succession has to start completely from scratch, such as in the case of a volcanic eruption, it is known as primary succession. But that is not the only form of succession. In some cases, well, actually in most cases, nature doesn't have to start completely from scratch.
Imagine the house gets completely flattened by a volcanic eruption. Everything is destroyed. Even the very foundation gets buried in lava. From this scenario, you would have to start completely from scratch, rebuilding the foundation, laying the framework, and I guess you know the story by now. Now imagine that instead of being completely flattened, the house just burns to the ground. In this scenario, the foundation stays intact, which means that you wouldn't have to start completely from scratch. The foundation can be reused. In nature, this process is known as secondary succession, when nature can reuse some of the key elements that survived. After a volcanic eruption, the landscape often becomes a mosaic of both primary and secondary succession. Some areas are buried under fresh volcanic rock, forcing life to begin anew, while others are only scorched by the heat and can pick up again from intermediate stages.
And in our modern world, this secondary form of succession is actually quite common.
Logging and other human-induced disturbances often place climate communities in an intermediate stage, and because of this, we call forests that have a history of logging secondary forests. Anyways,
when speaking of intermediate stages, this is a plant that we simply have to include.
This is a plant known as Anaphalis longifolia, or more commonly, just as Edelweiss. And it's perhaps the most specialized species you can find on this mountain. They live exclusively on Indonesian volcanoes, and they are perfectly adapted to the harsh volcanic soils. Just like the mosses, they release a bunch of organic acids, which helps free the minerals from the volcanic rock. But they also go a step further. Through their roots, they release special chemical compounds that attract a community of beneficial soil microbes, each with their own specific job. Some break down phosphorus-containing compounds, making this vital nutrient available to the plant, while others metabolize sulfur, helping detoxify the harsh volcanic soil just around the roots. In fact, studies have shown that the soil right around the plant's roots, an area known as the rhizosphere, contains almost 50 times less bioavailable sulfur than the surrounding barren soil. Furthermore, the plant releases compounds that are toxic to other plants, enhancing its own growth by inhibiting others. Because of these traits, ecosystems dominated by this species can become stuck in the intermediate stage of succession. Sometimes decades, even centuries can pass without changes in species composition. That's why on many of these Indonesian volcanoes, you'll find vast, almost monoculture-like stands of Edelweiss covering the slopes. Unfortunately, these incredible plants are in decline due to a rather surprising factor. See, if you were to pick a couple Edelweiss flowers, they wouldn't change much for a couple of years. This trait has made the Edelweiss flowers a popular souvenir for hikers and tourists, which means that the naturally occurring population has taken a serious hit. So, if you are ever lucky enough to see this plant, please just let it be. And with that said, we are getting to the point where things turn strange. Because the soil now contains minerals, it contains structure, it even contains organic matter, and yet the system still can't transition to a true climax forest. It's still missing a single but crucial ingredient: nitrogen. And honestly, it's kind of ironic, because nitrogen is just everywhere. Nearly 80% of our atmosphere is made up of nitrogen, so it really shouldn't be that difficult. But of course, there's a catch to this. The nitrogen in the air is locked in one of the strongest chemical bonds in nature. Almost nothing can break it. So the challenge isn't actually finding nitrogen, it's finding a way to make it usable.
And here's where this species comes into the picture. This plant is known as Parsbonia rigida, and it is one of the most important species on this volcano.
This plant grows small nodule-like structures on its roots. And inside these nodules, entire colonies of special bacteria are thriving. Here, they're doing something that only a select few organisms on the planet can do. They take nitrogen from the atmosphere and break it apart, transforming it into a form that the plant can actually use. In other words, they're turning air into fertilizer. And that changes everything. Because Parsbonia rigida doesn't just feed itself. As it sheds its leaves, or the plant eventually dies, those nitrogen-rich compounds are slowly released into the soil, becoming available for other organisms. And when that happens, the soil contains all the essential ingredients necessary for a rich and diverse ecosystem. Now all we need is time before this area becomes a climax community, with towering trees and dense layered vegetation. Unless, of course, Kelud decides to reset the cycle. But anyways, at this point we're getting very close to the summit, just a few hundred meters left. And this final part was definitely not easy. There's no trail, no steps, just bare volcanic rock. But eventually we made it. And wow, what a view. But exactly why are volcanoes so biodiverse again? You might not feel like I've answered that question just yet. And I haven't, at least not directly. And that's because the answer isn't actually up here, it's hidden in the descent. Once you know what to look for, then walking down a volcano becomes like walking backwards through time. Near the crater, only the hardiest pioneer species ever get the chance to establish. But as we move further away, we start seeing the intermediate species. And as we get further down yet, the forest structure will slowly but surely form a close canopy, reminiscent of a climax community. And this is the key to the paradox. Volcanic landscapes are rarely uniform. Instead, they are mosaics, patches of land in different stages of succession, shaped by the history of eruptions, landslides, lahars, fires, and everything in between. A single slope can hold everything from bare rock to climax forest. And when all those stages exist side by side, biodiversity increases exponentially. And this is exactly why these slopes can be so diverse. It's not in spite of the volcano's violence, but because of it. Without the eruptions, there would be no place for the pioneer species, and no opportunity for extremely specialized species such as the edelweiss. We tend to think of destruction and creation as opposites, but here they're the same process. The constant resetting isn't a flaw of volcanic landscapes, it's exactly what keeps them full of life. Which, I guess, is a paradox in and of itself.